2017 paper titled Attention is All You Need introduced this transformer architecture. While this architecture was originally proposed for machine translation, the same architecture has been basically copied and pasted in many other tasks, like for creating ChatGPT, creating vision transformers, etc. This architecture has several layers to it, like these feed-forward layers, add and norm layers. But the key part of this architecture are these attention layers. There are several attention layers. This video will be a definite coverage of these attention layers. We'll try to learn all the nuances and mathematical details about this attention layer. So let's get started. To start off, there can be four types of attention. There can be self-attention and cross-attention. This is one classification. There can be also single-headed attention and multi-headed attention. So in total, there can be four variations of this attention thing. One is single-headed self-attention or multi-headed self-attention. The other variation is single-headed cross-attention or multi-headed cross-attention. But if we can learn this one, single-headed self-attention, we can actually learn the later three within like minutes. So let's get started with single-headed self-attention. First, let's see what will be the input to the attention block. So the input to the attention block can be a sentence like this sentence, I have to go. But the problem is computers cannot understand sentences. Human can understand sentences. What computer can understand is numbers. So what we will do is we will convert each of the words of these sentences into vectors. So I will be converted into this vector, 0.1, 0.2, 0.3. Have will be converted into this vector. To will be converted into this vector. Go will be converted into this vector. Now in this example that I have shown, the vectors are of length 3, but in practice these will be much higher length vectors. But for example, we'll be considering these vectors to be of length 3. These vectors are what is called embedding vectors. So we have here 4 embedding vectors corresponding to 4 sentences. So the first step is converting our input to these embedding vectors. So we have 4 embedding vectors that we want to put into the network. And if we look at it, we can easily see that we can comprehend this as a matrix. And that's what we will do. We will interpret this set of 4 embedding vectors as a matrix. Specifically, each row of the matrix will contain a single embedding vector. So the first row of the matrix is this first embedding vector corresponding to I. The second row of the matrix is the second embedding vector corresponding to have. Third one is corresponding to 2. The fourth one is corresponding to go. So this matrix of embedding vectors will be the input to our overall attention block. So the input to the overall attention block is the embedding matrix, and the output will be another matrix. We'll go through the procedure of how the output matrix is produced from this input matrix. Now let's look at the attention function. This is the main thing. We will just simply be implementing this function to produce the output. So if we look at the function is attention equals to softmax of Q times K transpose divided by square root of Tk times V. So Q here is what is called query. K here is what is called key. And V here is what is called a value. So first of all, what we will do is we will create a key matrix from our input embedding matrix. So X here is our input embedding matrix that we just saw in the previous slide. So X here is the embedding matrix consisting of 4 rows corresponding to 4 words. So we will give as input our embedding matrix into a linear neural network to produce the key. We will input our embedding matrix into another linear neural network to produce the queries. We will input it into another linear neural network to produce the values. Then the keys, queries, and values will be put into this function and we will find our final attention. So first, let's calculate these 3 things: key, query, and value. So first of all, what we will do is we will give this input embedding matrix that we have into a linear neural network, and this neural network will give us as output the keys. So let's see what is the procedure. So each row of this input embedding matrix is one embedding. So we will put this row as input into this neural network. Now this neural network will have its weight. In this example I'm showing, it has 6 weights from W1 all the way through W6, and it has 2 outputs. Now this is an arbitrary thing that I have just shown for example. This can be 2 or 3, anything. For information, this is called the head size parameter. In this example I'm showing, I'm taking head size to be 2, but it can be anything. It can be like 4 or 5, something like that. And also these weights W1 through W6, they are trainable parameters. So they will be trained during the backpropagation of the network. So let's say just for example, the values of these weights are initialized as this, or at some stage of the training, the values of these parameters are as this. So there are 2 outputs of the network. We have set head size equals to 2. Let's know them as y1 and y2. So let's calculate y1. So to calculate y1, you can see y1 is connected with 3 edges. This one, and this one. So point 1 coming through weight 1 to y1. So 0.1 times w1 plus point 2 is coming through this edge w3 into y1. So point 2 times w3 plus point 3 is coming to y1 through this edge. So 0.3 times w5. If you put in these values of these weights here, we will find y1 equals to 0.13. In a similar fashion, we can find y2. y2 here is connected with these 3 edges. So 0.1 is connected to y2 through this edge. So 0.1 times w2 plus 0.2 times w4 plus 0.3 times w6. And if we put in these values of w, we'll find 0.52. So I found the first entry of our key matrix. So the key matrix, the first row of the key matrix will be the key value corresponding to the first embedding vector. So this is 0.13 and 0.52. Similarly, the second row will be what will be the output of this neural network for these embedding matrix. So let's go through that too. So now the input to this neural network will be this embedding vector. So 0.4, 0.5, and 0.6. And if we go through the same calculation process, now just for different input, we will find y1 equals to 0.34 and y2 equals to 1.28. So we find the second row in this key matrix, 0.34, 1.28. Likewise, for the third row, we'll find 0.54 and 2.05 is the output of this matrix. For the fourth embedding vector, we'll find the output as 0.74 and 2.81 if you go through the same calculation process. So what we find finally is this. This is our final key vector that we have gotten. This is the final key matrix that we have gotten. Now remember that the first row of this key matrix corresponds to the key of the first embedding vector. The second row is the key corresponding to the second embedding vector. So just keep that in mind. So we have found the key matrix. Now it's time to find the query matrix. So this is our input embedding matrix, and we'll put this through another neural network, query neural network. and we'll produce the query just as before. So first of all, the first row of the input embedding matrix will be put as input to this network, 0.2, 0.2, 0.3. And then it will go through this neural network. This neural network will have weights associated with it. Now this is a different neural network, so it will have a different set of weights associated with it. And obviously again, these are trainable parameters. These weights will be updated at every iteration of the training. And we will get output. So for this row, the output we'll get will be 0.23 and 0.26. And this will create the first row of the query matrix. Then we'll put as input the second row of the input embedding matrix, 0.4, 0.5, 0.6, 5, 5.6. And just as before, with the same calculation process, we'll find the second row. Then we'll put as input the third row. We'll find the third row of the query matrix, fourth row of the query matrix. So this is the final query matrix that we get. It's time for the final one. We'll go through the same procedure. We'll just use a different linear neural network with another set of weights going from W1 through W6. And remember, as we have head size equals to 2, we have only 2 output of this neural network. So first, this row will go as input in this neural network, and we'll find one set of input. Then this row will go as input, and we'll find another set of output, this one, another set of output. And just as before, going through the same procedure, we'll find the fellow matrix as this. So now that we have calculated the query matrix, the key matrix, and the fellow matrix, we can calculate the attention. So we'll first calculate query matrix multiplied with the transpose of the K matrix. And then there is an additional step, scaling by square root of dk. We'll go into this step after a while. So first, let's go through this matrix multiplication. So this is the query that we have. This is the key that we have. And we are trying to perform this operation, query times K transpose. So first, let's define the transpose of K. And this will be the transpose of K. Transpose equals to this. Finding the transpose is very straightforward. We just make the first row into the first column, the second row into the second column, and likewise. So now performing query times K transpose, we just simply perform these matrix multiplication. Now this is the heart of the whole attention thing. This matrix multiplication is where actually the attention thing is going on. First, let me just show the matrix multiplication mathematical part. Then I will explain how this is actually doing the attention thing. So if you do the matrix multiplication, we'll find this as the output. So if you don't remember how matrix multiplication is performed, so this is how it is done. We will multiply the first row with the first column to get the first element of the result. If I show it here, so the first row is 0.3, 0.23 will be multiplied with 0.13. So 0.23 times 0.13 plus 0.26 will be multiplied with 0.52. 0.52, and this will give us as output 0.17. And likewise, the first row will be multiplied with the first row will be multiplied with the second column. Find the second element here. Then with the third column to find the third, likewise the fourth. And the second row will be multiplied with the first column to get the first element of the second row here. So I think it's clear how the matrix multiplication is done. So now to the main question, that how actually is it performing the attention thing? Now, as I pointed out to you earlier on, this first row is the query corresponding to I. Okay, so let me point it out here. This is the query corresponding to I. This is the query corresponding to the embedding vector of have. So we can say this is the query corresponding to have. This is the query corresponding to go, this third row, and this is corresponding to go. But the key part, this first row, is the key corresponding to I, second one have, and so on. So when we transposed it, the first row has become the first column. The first column is the key corresponding to I. The second column is the key corresponding to have, and likewise. So we write it here. I have to go. Now, when we're finding this first element here, 0.17, what we did was we multiplied the first row of the query matrix with the first column of the key matrix. Now, if you remember this from your linear algebra class, matrix multiplication is basically a dot product. So this thing that we did, this thing that we did is essentially the dot product of query of I with dot product with the key of I. And when we're calculating this second element, the second element 0.41, what we're essentially doing to find it is the query of I, the first row here, times the second column here. The second column here is the key of F, key of F. And what does dot product do? Remember from your linear algebra class, what dot product finds is how close two vectors are. So in geometric plane, if this is one vector and this is another vector, they're completely in the same direction, the dot product will be equals to 1. If this is one vector and this is another vector, you can see that they're in completely different directions, so the dot product will be equals to 0. And if this is one vector and another vector is going in the complete opposite direction, the dot product will be -1. Likewise for intermediate value, if they are closer, the dot product will be close to 1. So this will be something like 0.9. If they're farther apart, the dot product will be small. For example, in this case, it will be something like 0.2. So what dot product does is that it finds how close two vectors are. So when you are producing the dot product of query of I and key of F, what you're essentially finding out is how related these two words are. So remember that I and have, you can think of these as a representation. The query of I and the query of have, you can think of these as a representation of I and have. So when you're performing the dot product, what we are finding out essentially in this vector, the second element is signifying how close the two words I and have are, or how correlated they are. Or in other words, this element here, 0.41, is the value of I attending to have. This is signifying I attending to 2. So this was produced by I, this first row, multiplied by this third column. So this is finding out I attending to 2. This is finding out I attending to go. So we can interpret this whole procedure as such. We can interpret this whole procedure as such in the so this first element is I attending to I. The second element is I attending to have. This third element, 0.66, is I attending to 2. Likewise, this element, 1.11, is go attending to I. This element, 2.76, is go attending to have. Let me reiterate it again. How is this element go attending to have? Because to find this element, 2.76 here, what you did was you multiplied this fourth row with this second column. This multiplication produced this element. So you basically did a dot product, and what this dot product found out for you is how correlated these two vectors are. So I think this is clear to you that how performing the dot products are actually, so I think this is clear to you how attention is actually just the dot products of two vectors. So I've just gone through the most important part of the whole attention mechanism, which is the multiplication of query times key. Now our second step is dividing the multiplication result by square root of dk. So what is dk? dk is the embedding dimension. So each of our embedding vectors was of dimension 3. So in our case, dk is equals to 3. So what we will have to do is, this is our multiplication result. We'll have to divide q times k transpose by square root of 3, as our dk is 3. And the result we'll find is this. It's just simple matrix multiplication by a scalar. Now, why we're doing this actually, I will not go into the detail of why actually we're doing this, but just keep in mind that it helps in keeping the model straightforward. Now, why we're actually doing it, I will not go into the detail of why we are scaling the matrix multiplication output, but just remember that this helps in keeping the numerical stability in the whole process of training. The next step is applying the softmax, but before applying the softmax, there's something called masking. It's an optional step. This is not actually applied in all types of attention. If you look at the transformer architecture here, this in the decoder part we have masked attention, but in the encoder part we have no masking. So in the decoder part we need to apply masking. As this is not a mandatory part as of now, I'll not go into this. This maybe seems like an extra thing and might overload you. We will look into this thing at the later part of the video. From now on, let's keep masking as this is an optional thing. Let's move on to the next step. So now that we have found the scaled multiplication result, the next step is applying softmax on the result. Now this is the mathematical representation of the softmax function. It may look very fancy, but softmax is a very simple function actually. Let's have a vector y as 3, 4, 6. We will find the softmax of y. Softmax of y will be another vector of the same dimension. So softmax of y will have 3 elements too. To find the first element of the output of the softmax, what we do is e to the power the first element of the input vector, e to the power 3, divided by e to the power 3 plus e to the power 4 plus e to the power 6. That is e to the power summation of e to the power of all the elements of the y matrix. So let's just say it gives us the output. So this gives us an output of 0.04. So the first element will be 0.04. Find the second element of y vector is 4. So we put e to the power 4 divided by e to the power 3 plus e to the power 4 plus e to the power 6. And we calculate this, and the result comes out to be 0.11. So this will be 0.11. Finding the third element is the same procedure. The third element is 6, so it will be to the power 6 divided by sum of all the e to the powers. And this will give us the output of 0.84. So the third element will be 0.84. So this is the softmax function. This is a very straightforward function, nothing fancy here. So let's apply it on our multiplication result. So here is our scaled multiplication result, and we will apply the softmax function row by row. So we'll apply the same procedure just we've seen on this row, and then on this row, and so on. So when we apply the softmax function on this row, we will get this one, the second row, this one, the third row will be transformed into this one, and so on. Now the question is, what does the softmax function actually do? What is the benefit of doing this? So what the softmax function does is that it converts each row into a probability distribution. So what it has done is that this row has become a probability distribution. That means is that the sum of all the elements in this row will be equals to 1. So if we sum these elements 0.20, 0.23, 0.27 plus 0.31, we'll find 1. You can sum likewise all the other elements of all the other rows, we'll find 1. So this means that the 0.20 is now a probability. 0.23 is now a probability. So the interpretation will be like this. We just saw that that this element 0.14 was the value of 2 attending to have. Now there is a probability. This element will mean the probability of 2 attending to have. Likewise, this element will mean the probability of I attending to I. So all that remains is the very last step of the attention function. We found the softmax of the matrix multiplication. We're not yet done. We have just one step remaining, and that is multiplying the whole thing with the value matrix. Remember, we found the value matrix by putting our embedding matrix into a value neural network. So we just multiply the result of the softmax with the value matrix, and this is a matrix multiplication. And for the matrix multiplication, what we get is our final value of attention. This is our final value of attention. So that's it. That is the whole procedure. And if we summarize, what we have done so far is that we had an input embedding matrix. We put that through a key neural network and found a key. We put the same input embedding matrix to a query neural network and found a query. Found the same input embedding matrix into a value neural network, and we found a value matrix. This key, query, and value all are matrices. Then the keys and the query matrices were put into a softmax function, and the output of the softmax was then multiplied with the value. And remember, this is matrix multiplication. This is not an element-wise multiplication. The output of the softmax was matrix multiplied with value to give us the final output. So that's it. That is all about the self-attention mechanism. So we have covered single-headed self-attention. So what's remaining is multi-headed self-attention, and then also the two variations of cross-attention. We will discuss about them in the next video. In the last video, we learned about how self-attention works. It will now become very easy for us to understand multi-headed self-attention and cross-attention. So let's start with multi-headed self-attention. Now remember what we did for single-headed self-attention. We took an input embedding matrix which represented, say, a sentence. The input embedding matrix was put as input into a key neural network, into a query neural network, and into a value neural network. The output of the key and the query neural network was then put into a softmax function. The output of the softmax function was then matrix multiplied with the output of the value neural network, and the result of the multiplication was our final attention matrix. In multi-headed attention, we will do the same operation, but with a different set of key, query, and value neural networks. So what we will do is we will put as input the same input embedding matrix into a new key neural network, a new query neural network, and a new value neural network. Then using the keys and the queries from these networks, we'll calculate the output of the softmax function just as we did in single-headed self-attention. Then the output of the softmax will be multiplied, matrix multiplied with a value to produce the final attention output. So this is our final attention output from this block, and then the attention output of block 1 and block 2 will be concatenated together to produce our final attention. Now look at the concatenation. It's a very simple concatenation. It's just these two matrices put side by side. So if you notice, this is this first matrix, and on the right side this is the second matrix. It's just two matrices put side by side. So each of these blocks will be now called a head. So this is head 1 and this is head 2 of our attention. There you go. This is a multi-headed self-attention with two heads. Now, a natural question that arises is, why would you want to use two heads? Or if you want, you can actually add more heads here. You can add 3, 4, as many heads as you want. The question is, why would you want to add more heads? The idea is that every head has its own key, query, and value neural networks. So these key, query, and value neural networks, they can learn. They're learnable networks. So the idea here is that every head's networks will learn about different features of our input embedding vectors. So for example, head 1 can probably learn about how nouns work in the language. Head 2 can probably learn about how pronouns work in the language. Then subsequent heads can learn about other features of the language. So this is how it is interpreted. Usually in practical attention networks, several heads are used, like 8, 16, or even more in the lattice attention networks. Before we move on to cross attention, I'd like to point out one thing between the relationship of head size, number of heads, and embedding dimension. Now, just to point out, remember what head size meant. Head size was the number of neurons in each of the key VELU and query neural networks. The number of neurons in the output layer of each of the key query and the VELU neural networks. So in our example, we used a head size of 2. And remember what embedding dimension meant. Embedding dimension was the number of elements in one embedding vector. So in our case, it was 3. So we did not use same number for the head size and embedding dimension. Now, in usual convention in neural network, the number of head size is kept equal to the embedding dimension. It's not a must, but it's better for keeping dimensional consistency in the model. So remember, for single-headed self-attention, we would keep the head size equals to embedding dimension. And if we're using multi-headed attention, we would keep the head size equals to embedding dimension divided by number of heads. So for example, say we are using an embedding dimension of 54, and we are using 4 heads in our architecture, then the head size should be 54 divided by 4, which is so for example, say we're using embedding dimension equals to 56 and we are using 4 heads, then our head size should be 56 divided by 4, which is 14. Now that we have learned about self-attention, both the single-headed and multi-headed variant of it, let's learn about cross-attention. In self-attention, we worked on only one embedding matrix, but in cross-attention, we will work on 2 embedding matrices. Now, what might be the case where we will need to work on 2 embedding matrices at once? The classic example is language translation. Let's say we have a sentence in the Bangla language, is read as Amar jete hobe, and we have to translate it into English. The English translation is I have to go. So this is our source sentence, and we have to translate it into our target sentence. So in cross-attention, we will have 2 embedding metrics. One is our source embedding matrix corresponding to our source sentence, and the other one is our target embedding matrix corresponding to our target sentence. So the source embedding matrix will be used to create a source VELU using a VELU neural network, a source query using the query neural network, and the source embedding matrix will be put into a key neural network to generate source key. Similarly, the target embedding matrix will produce a target key, it will produce a target query, and it will produce a target VELU. Now, obviously, the key neural network used in the target side will be different from that used in the source side. These are different neural networks. Now, to calculate the output of the softmax function, here is the trick, here's the difference. Into the softmax function, the query of the target will go, and the key of the source will go. And then the output of the softmax will be multiplied with the VELU of the source. So the new formula that we get for cross-attention is softmax of query of target times key of source transposed divided by square root of dk times value of source. So to calculate cross attention, we will use the query of target, but the keys and the source, the keys and the values of our source. That is the only difference, but the overall formula, as you can see, is same. Now, what is the cross attention thing actually doing if we think about it? Now, remember, for self attention, our attention worked like this. We used a table like this to show it. Let's say I have a sentence I have to go, and I'm applying self-attention on it. So remember, what self-attention did was it gave attention between different words of the same sentence. Different words of the same sentence. So the self-attention matrix coming out for this sentence would be a 4x4 matrix. And this 4x4 matrix, if I said what this element meant, this element would have meant the attention between the word have and I. What this element would mean, this element would mean the attention between the word go and to. Now in cross attention, we have two sentences or two embedding matrices. So here, the output matrix has the source has 3 words and the target has 4 words. The output matrix will be a 3x4 matrix. 3x4 matrix. And what did the first element mean here? What the first element mean here? This would mean the attention between Amar and I, these two. But the second element mean this would mean the attention between Amar and have. So this is giving attention across two different embedding matrices, and that's why it's called cross attention. So every word of our source sentence or the source embedding matrix is being attended with every word of our target sentence or target embedding matrix. And that's it. We're done with all the different types of attention and how the mathematics actually go behind it. And if you notice it, the math actually is not that much harder. It's not something very fancy. It's just some dot product and matrix multiplication and a softmax function. But what this can do is unbelievable. Models like ChatGPT, Gemini, or Translatedtron, all these models work based on this architecture. And now if we look at the basic 2017 Attention is All You Need paper, this is the architecture they used back in 2017. And let's look at the different attention blocks here. First of all is the multi-headed attention. Then here is a must multi-headed attention. And this is a cross attention block. So these two were self-attention block. This is a cross attention block. If you notice here, the queries and the values are coming from the left side. This is the encoder block. And the if notice, the key and the value is coming from the encoder side, the key and the value, and the query is coming from the decoder side. So this is a cross attention. So self-headed attention, multi-headed attention, and cross attention. We learned about all of them. So before finishing up the video, I'd like to point out some notes about transformer models in practice. So first thing to note out is that embeddings are actually not created for every words. This is a misconception that people have at the beginning This is a misconception that people have at the beginning. But embeddings are not actually created for every word, they're created for every token. And what actually is a token, it's out of the scope of this video. Maybe in some future video I will talk about it. A token can be a word, it can be a part of a word, or it can be several words together also. So a token, you can consider it as a set of characters. It may not be a word, just keep that in mind. And the second thing is the practical models are scaled much bigger. So for example, in the GPT-3 175 billion parameter model, the embedding dimension was 12,288. And in our example, we used an embedding dimension of 3. So it's doing the same math, but it's just scaled much larger. And GPT-3, the number of heads they used was 96. So the head size, as we saw in the formula, is embedding dimension divided by number of heads, which is 128. So just keep that in mind. So real big models like ChatGPT, Gemini, or whatsoever, they're just doing the same math that we learned in this video, but it's just scaled much, much bigger. That's all about Transformer.